what is WebAssembly? For that, we need to go back in time a bit. And I know this came up a couple of times already, but let's just do a quick round of the history of the web. So first we had some websites, and in 1995, JavaScript was invented. And people started using it to extend their websites with some dynamic features, making certain things more interactive. Back then, JavaScript engines were quite simple interpreters. And by today's standards, they were quite slow to execute the code, but it was completely enough for the task at hand, just animating some things or making things more interactive. But people started using it more and more, and they ran into problems with it. And at some point, it was just too limited. It was only confined to be run in the browser. It couldn't interact with things outside of the browser, and there were no APIs to do this stuff. So people used something else. And that's how we got Flash and Java applets. People used those to do things they couldn't do with JavaScript, build even more interactive things, stream video, play games in the browser, and so on and so on. But they also learned about the problems doing this when it's not really integrated into the web world. We hit roadblocks, we hit security problems, and we hit incompatibilities between all these things. So people again moved back to use JavaScript more and more, and they took the ideas they had from Flash and Java and built web APIs into the browser so that they can use them from JavaScript. But JavaScript was still not the fastest thing in the browser. But this changed in 2008 when V8 was released, which was basically a new engine that JIT compiled some of the code and ran it much faster in the browser. And that's when we got more and more stuff that was moved to the web. We got huge web applications. We got full-blown mail programs. We got image editors, maybe even video editors in the browser, because the engines were fast enough to execute that. But people weren't too happy with writing JavaScript all the time, so they also used other languages and tried to turn that into JavaScript at some point and execute it in the browser. And even though that worked, it was not optimal, because JavaScript was not intended to be a compile target. But people thought about how they could simplify that and optimize that so it can run as fast as JavaScript that was natively written. And that's how we got asm.js. asm.js started as a project which was also sponsored by Mozilla, and intended to standardize a low-level subset of JavaScript with a few certain features that would make it enable engines to actually run this code as fast as possible. As such, it would be a compile target for other language. So it would take your code, compile it to asm.js, and run it in the browser without much loss of speed. So let's look at two features of asm.js that make this possible, because they're quite relevant to WebAssembly today as well. Consider this simple JavaScript function, add, which takes two arguments, x and y. Adds them together and returns the result. For us, this looks quite simple. And if you input two integers, that is actually quite simple. It only needs to call the plus operator on two integers. If you put two strings in there, you have a whole nother operation there. The plus operator on strings in JavaScript is defined as concatenating those two strings. So the engine now needs to decide what to call. And once you start putting in something else than a string or an integer, like an object or an array, well, things will happen that you don't want to happen. So what we can do to make this more efficient is tell the compiler what we expect here, or the engine what to expect to execute here. And we only want to execute it on integers. So why don't we tell it to use integers? There are no types in JavaScript, so we need to have something else to make it like a type. And that is a type annotation. We can binary OR a variable with 0, and we don't change the value at this point. But because a binary 0 only makes sense if you're using integers, the engine also knows that it has to expect an integer. And without changing the value, we can drop down to the efficient code that just adds two integers. If the engine can detect this, it can just drop down to the actual machine code that adds to integers and can be fast. And that's what asm.js tried to standardize as well. So when you compile code, it would look similar to this. The other big thing asm.js did was providing a linear memory buffer for all your data. If you're programming JavaScript, you most of the time don't think about your memory usage, because the garbage collector will eventually come around and collect all the garbage that there is and free the memory behind that. From time to time, you might run into problems with that, but most of the time, you don't care. But this also means that the garbage compiler actually has to stop running your code at some point, look what is there to be freed, free that memory, and then continue running your code. This can make your execution quite unpredictable, because you can't control when these stops happen and when the garbage is collected. And for certain applications and algorithms, these performance problems can be quite severe. So what asm.js did differently is, instead of using JavaScript objects and references them all over the place, it uses one large memory buffer. From the point of view of the engine, this memory buffer is always in use, so it won't get garbage collected, right? Now you can put in your data into this memory buffer, and you're now responsible for handling this memory in the buffer, but it won't get erased from the outside. If you're coming from a C background, or C++, or even Rust, this might sound much more familiar, because it neatly maps to how the heap is handled, or memory is handled in C. So with this layer, we can easily translate the semantics of C to this asm.js. But not all browser vendors agreed to implement this in their engines, and not everyone agreed on all parts of it. So it never got the full spread that we would love to have. But people sat down and thought about these ideas, and what came out is Webassembly. Webassembly became a W3C group in 2015 with everyone involved. So what is Webassembly? Well, it's a lot of things. First off, it's a new binary executable format for the web. It will allow you to take your code written in another language, turn that into WebAssembly, and then run it in your browser without you ever having to deal with JavaScript directly. But WebAssembly is also a general-purpose virtual architecture. That means it gives you a few operations and the semantics of these operations, but none of these operations are directly bound to the architecture of your system. But they're also laid out in a way that it's quite easy to translate them to the system underneath. So it's quite easy to go from WebAssembly to the actual hardware machine instructions. And while it is intended for the web, there's nothing in the specification that bounds it to the web. You can have a self-implemented architecture where you don't deal with any JavaScript or browser stuff. And this architecture also allows it to be implemented on top of other engines. And browsers actually did that and just reused the existing JavaScript engines, which are by now only compilers anyway, so they can run WebAssembly code as efficiently as possible. And as mentioned before, WebAssembly is a compiler target. So the idea is that you can take your C code or C++ or even Rust code, throw that into your compiler, and out you get a WebAssembly module. At least that's the idea. We are not really at that point that it just works like that. WebAssembly is also an open standard. It's developed by a W3C community group, and every browser vendor is actually involved in this group. The first version of WebAssembly was stabilized earlier this year. And by now, it's implemented in all major browsers. So in Firefox, in Chrome, in Edge, and in Safari, it's available. And as far as I know, even in mobile Safari. So you can test it out now on all your devices. When speaking about WebAssembly, though, we also need to speak about what WebAssembly is not, because people tend to confuse those things. WebAssembly is definitely not a replacement for JavaScript. It will happily live side by side with JavaScript, And I'm pretty sure that the majority of web applications out there won't be rewritten in WebAssembly anytime soon. We will get more applications and more libraries that make use of WebAssembly, but you can still rely on your plain old JavaScript. WebAssembly is also not a programming language by its own. You sort of can write it manually, but just as you wouldn't write assembly anymore, you probably don't want to write WebAssembly either. You compile to it. WebAssembly is also not a target for every language out there, at least not yet. There are too many missing features that would make things with bigger runtimes possible on that. The things that don't have a large runtime on their own, like C or C++ or Rust, are a perfect target right now. With all this information, you might wonder, why can't we just use asm.js? I mean, there's everything in there, and it indeed has advantages. After all, it's just JavaScript. Every browser should be able to execute asm.js anyway. And it's quite fast, at least in these browsers that implemented certain optimizations for asm.js. But there are disadvantages as well. First off, there is no fully agreed formal specification of asm.js that one could follow. And even though it's fast in some browsers, there are no guarantees that you will hit this optimized path. And it's very hard to extend. After all, it's just JavaScript, so we can only use what's in JavaScript. We can't just add certain features like threading or bigger integers that we want to have in a new target. So, why WebAssembly? Well, it's intended to be smaller than asm.js. It's a binary format with certain encodings that makes it quite small. And it's easier and faster to parse. JavaScript is actually quite hard to parse. And on the other hand, with WebAssembly as a binary format, you mostly need to run through the binary data, check that it's encoded correctly, and then you can compile it down to the native code. And WebAssembly as a new platform now gives us the chance and the freedom to extend this with the features we want. And as mentioned before, there is a formal specification that all browser vendors and all implementers agree on, so we can be assured that it will be implemented in all browsers the same way. So I will give you a few use cases where it actually would make sense to have WebAssembly. And after that, I will also show you what WebAssembly would look like if you're actually going to use it. So the first thing that comes into mind when you're doing anything that has performance in the browser, the first thing that pops up are always games. With WebAssembly, it would be possible to compile a huge 3D game, put that in your browser, and play it without ever installing it. Of course, you still need to download the resources, but it will run in the browser without any installation. And there are demos out there using the Unity engine or other engines that make this possible. Certain other multimedia applications come to mind as well. Image or video editing can be improved using WebAssembly. Or even live video augmentation can really use the performance that WebAssembly would offer. You also saw the live video from the demo before, where once I switched to WebAssembly, it was quite a lot faster. Or other 3D or CAD applications could be extended using WebAssembly. And speaking of performance, everything that requires that, like encryption or machine learning or full platform simulation, if they would use WebAssembly, it could all run in the browser, on your laptop, on your phone, or any other device that can execute this. But WebAssembly, again, is not bound to the web. For example, the blockchain Ethereum is having ideas about using WebAssembly as an execution platform for their smart contracts. That does not require the web. And another quite interesting example I found was a medical image file format, which is quite old. It's open, but most libraries and applications are not, and are bound to quite old operating systems. So someone took this, wrote a thing that he compiled to WebAssembly, and he's now building a whole application around that. So it can be used in the browser, but it could run somewhere else as well. Now, let's give let me give you a quick walkthrough how you can use WebAssembly today. Because even though it's used just the compiler, there are a few more steps involved to fully understand that. If you really want to get started today, you probably want to take a look at mscripten, a project that was started when asm.js came up as well. It's basically an LLVM-based compiler that can take C, C++, or now even Rust code and compile that to JavaScript, to asm.js, or even WebAssembly now. So once you got that, you can take your C code with this very complicated function called half, taking an integer x. It divides that by a constant number 2 and returns the result. Now, if you want to use that in your native application, you would call your compiler Clang or GCC, pass some flags, and you get an object file out of there. That one you can link to some other application that can then halve numbers easily. If you want to do the same with WebAssembly, you need to call mscripten, pass a few more flags, and tell it to output a WebAssembly module. And out you get this. This is the binary representation of WebAssembly. And this is what actually would get delivered to your browser. Let's quickly step through what's in there. WebAssembly always has a magic header indicating that it's WebAssembly, so your browser can do the right thing. It's then followed by a version number, which is currently version 1. And with additional features, this will probably increase. Further down, you then see the export section. So WebAssembly module can always export stuff. And that's by name, so you can actually access that from the outside from your JavaScript site. And last in the file, you have the actual code. And to divide the number by 2, all it takes are these 6 bytes. Luckily, we as humans don't need to understand these raw numbers, but we can look at the text format of WebAssembly as well, called what. What is a one-to-one mapping of the binary code to some list-like structure that will show the same code. So again, we see some metadata, we see our export of our function, which actually points to code somewhere else in the file, and further down you see some assembly-like instructions getting the argument and the constant number 2, calling the diff operator, and the result will actually be returned. Now, to actually call this from the browser, there's a new web API as well, where you first need to fetch the data from the server. Then you tell the engine to compile this code, instantiate it, and then you can access the exports. And if we call the function half on 128, we actually get 64, as one would expect. Now, if you're more into Rust, like I am, don't worry. It's quite easy by now to use that from the Rust side. Hit me up if you want to know more about that, or go to hellorust.com/wasm. In the future, this will hopefully change even more, so you don't need to know all the details, what to call. And if you're already using Webpack, I have high hopes that they will make it much easier to integrate WebAssembly into your applications. Basically, the idea is that at some point, you can just drop the Rust files into your application folder, call Webpack, and then it will do all the rest for you. Before ending this talk, I also want to give you an outlook of what WebAssembly has to offer in the future. WebAssembly was always made with the idea in mind that the very first version that gets integrated into a browser is only the basis. So additional features were planned from the beginning, but weren't integrated into that because they required more design work, more implementation work. But they are always there. One big thing that comes to mind is thread support. In native applications, it's not that hard anymore to use all the cores in your application. While writing threaded code is still hard, the APIs in native applications are there. Now, we don't have the same in JavaScript, but we will get something similar in WebAssembly at some point. By basically putting everything into web workers and connecting this through shared memory, we can do something quite similar to threading. And applications that would otherwise use threading when compiled natively perfectly map to this concept as well. There is also support planned for SIMD support, which basically will use certain math operations that are implemented in your hardware already to speed up calculations. And this will get to WebAssembly as well, making it quite faster. But to succeed in a world of the web, WebAssembly needs integration into what's already there. That means it needs integration into the existing web APIs. It needs access to the DOM. And it, at some point, also needs integration into the garbage compiler of the engine that is actually executing it. This would allow better interaction between JavaScript and WebAssembly, but also allow languages which with a larger runtime and a garbage collector of its own to be integrated into this whole ecosystem. So let me end by some quotes of Dan Callahan, who said that if you're a native developer like me, for example, the web is now just a compiler target away. If, on the other hand, you're a web developer, like a lot of you, you can now leverage the enormous world of native libraries that it's already out there. But both worlds now have to learn from each other to make the most of this and to make this work. Thank you.